Hello, we'll be solving problem 2 from 0.2 exercises. And the first problem says, the sum of the first two integers. And what I wrote is, this is not a statement because it does not make sense to assume that the statement is either true or false. For B, everybody needs someone sometime. This is an atomic statement because it cannot be divided into smaller statements. And according to the statement, there are some quantifiers but no connectors. C, the Broncos will win the Super Bowl, or I'll eat my hat. So this is a molecular statement, specifically a disjunction because the statement is expressed as P or Q, which can be written logically as PVQ. Although if we read it into a bit more, what the speaker is really saying is that if the Broncos do not win the Super Bowl, then he will eat his hat, which would be a conditional statement and can be expressed as if P, then Q. Problem D, we have donuts for dinner, but only if it rains. This is another molecular statement, specifically conditional as it is expressed as if P, then Q. E, every natural number greater than 1 is either prime or composite. This is an atomic statement, even though there is an or in the statement, which is right here. It would not make sense to consider the two halves of this disjunction. And F, looking at it, you probably think that it could be a statement, but in fact, it is not. Although it certainly looks like one, once again, the statement must be true or false. If the statement was true, that would make it false. If the statement was false, that would make it true. Moving on to problem 8. And it says, consider the statement, if Oscar eats Chinese food, then he drinks milk. So for problem A, it says, write the converse of the statement. So I wrote, consider the statement, if Oscar eats Chinese food, then he drinks milk. So the converse of this statement would be, if Oscar drinks milk, then he eats Chinese food. And note, to form the converse of the conditional statement, interchange the hypothesis and the conclusion. B, write the contrapositive of the statement. And the contrapositive can be written as, if Oscar doesn't drink milk, then he doesn't eat Chinese food. And note again, to form the contrapositive of a conditional statement, interchange the hypothesis and the conclusion of the inverse statement, thus making the statement opposite. Problem D, suppose the original statement is true and that Oscar drinks milk. Can you conclude anything about his eating Chinese food? Explain. So, problem C, is it possible for the contrapositive to be false? If it was, what would that tell you? So first, with C, it says, if the provided statement is true, then the contrapositive is logically equivalent to the provided statement. And if the provided statement is false, then the contrapositive is always false. And now D, suppose the original statement is true, and that Oscar drinks milk, can you conclude anything about his Chinese food eating habits? So D, let the original statement be true, and we know that Oscar drinks milk, then we still would not be able to make a conclusion of the matter of him eating Chinese food. So in this case, I have, suppose P is Oscar eats Chinese food, and Q is then he drinks milk. So logically, it can be written as if P, then Q. And no, if P then Q is true when P is false, and Q is true or both. So in this case, since we know that Oscar drinks milk, which is Q, is true, then Oscar eats Chinese food is either true or false. which is why a conclusion cannot be made. And lastly, problem E. It says, suppose the original statement is true and that Oscar does not drink milk. Can you conclude anything about his Chinese food? His eating Chinese food again. So, suppose that the original statement is true and that Oscar does not drink milk. It means Oscar doesn't eat Chinese food, because if Oscar eats Chinese food, then according to the truth of the original statement, Oscar drinks milk to be true, which is a contradiction. Thus, Oscar doesn't eat Chinese food. Now we're moving on to problem 10 from section 0.3. In the first problem, A says, find A intersecting B. So, A intersecting B consists of the elements common to both set A and B. So therefore, A intersecting B would just be 4, 6, 8, 10, and 12. Problem B. It says, find A union B. And in set A and set B consists all of elements. Thus, A union B would have 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, and then 16, 18, 20, and etc. For this case, A union B consists of all even numbers and the odd numbers, which is written all here in set A. All right, C, find B intersecting C. So B intersecting C consists of elements common to both set B and set C. So clearly B intersecting C is an empty set. So this is because no element is common to both sets, as set B consists of all even numbers and set C consists of all odd numbers. So a number can be either even or odd. Lastly, D, find B union C. So B union C consists of all elements in set B and set C. Therefore, B union C is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and etc. Keep on going infinitely. So we can observe that this is the set of all natural numbers. Now we're on 15 from section 0.3. And it says, draw a Venn diagram to represent each of the following. So this time we'll draw each of these that's displayed. So for problem A, it says A union not B. And here I drew it out in steps. So for A, we will shade all this. And for not B would be everything except for B to be shaded. So everything from this side would always have to be here. And it could be the opposite. If it was A, not A, then everything would be shaded in the B region. So A union not B, we can conclude from gathering all of this would be this, all this shaded. All right, so B, A union B, so not A union not B, can be expressed as this. So not A would be all of this region shaded, and not B, all of this region shaded. So since we have not A and not B, it will just be nothing. Just be blank. Nothing will be shaded since everything is not in each side. (15C) I did change a little bit, and I put B intersecting A union C. So A union C, naturally you would shade all of this, but you want it to intersect B. So therefore we will shade all of this region. And for D, it says A not in B. No, A intersecting B in union C. So A intersecting B would be this. We will shade this region. And then it says union C. So then we will shade all of this. Problem E, not A intersecting B, not intersecting not C, or the complement of C, another way of saying it. So from this problem, we will shade all this region here. And lastly, 15F, I changed a little bit again. I put B union C, not A. And B union C will be all this shaded. But we didn't include this part because A is included as well, as it says not A. So we'll just shade only this region. Lastly, we're on section 0.4, starting with problem 2. And it says, the following functions all have the set of 1, 2, 3, 4, and 5 as both their domain and codomain. For each, determine whether it is only injective, only surjective, bijective, or neither injective nor surjective. And as we can see, for 2A, we have F equals, and we have the codomain as 1, 2, 3, 4, and 5, and the domain as all threes. So this would be neither injective nor surjective, because it is not injective because more than one element from the domain has 3 as its image, as you can see. It is not surjective because there are elements of the codomain 1, 2, 4, and 5 that are not images of anything from the domain. Now we have B. So judging by this problem, looking at it, we can see that these numbers, the codomain and the domain, all have the same numbers. So this would in fact be a bijection because every element in the codomain is the image of exactly one element of the domain. C, fx equals 6 minus x. So this can also be written as 1, 2, 3, 4, 5, and 5, 4, 3, 2, 1 in the domain and codomain. So this will once again be a bijection because note, we could write the function in two-line notation as this, as it expressed like this, since they both will have exactly the same elements in the domain and codomain. Lastly, problem D, we have fx equals x divided by 2 if x is even, and x plus 1 divided by 2 if x is odd. So we can write this function in the two-line notation, which it could be expressed as 1, 2, 3, 4, 5 in the codomain, and in the domain we have 1, 1, 2, 2, and 3. So from this, we can quickly see it is not an injective. For example, 1 is the image of both 1 and 2, nor surjective. For example, 4 is not the image of anything. So lastly, we have problem 10, and it says, suppose this function satisfies the recurrence of fn plus 1 equals fn plus 3. So note that this is not enough information to define the function. Since we don't have an initial condition, for each of the initial conditions below, find the value of f5. And we have A, starting with A, it says f of 0 equals to 0. So this is how you'll solve the problem. So we started with f1. So f1 will equal f0 plus 1. And then we will equal it to f of 0 plus 3, and we get the value of 3. And now since we have that, for 2, we can put 3 in for this spot and add it up and get 6. And notice it keeps on going up by 3 and 3 and 3 and 3. So it keeps on adding up by 3. So we can assume for 5 that eventually, so 5 times 3, it would be 15. And now lastly, for problems B, C, and D, all you really need to do is add 15 with each of these numbers. So for problem B, the answer would be 16. C would be 17, and D would be 115.